everything we've talked about so far, we've been talking about two-tailed tests. Now, a two-tailed test is when we have a null hypothesis that the mean equals a specific value or the difference in means equals a specific value. And our alternative hypothesis is that it's not equal to that value or not equal to that specific difference. That meant that if it was either higher or lower in an extreme enough way, then we rejected our null hypothesis in favor of our alternative hypothesis. Now, sometimes we're only interested in a single tail, so we're only going to reject if our value is too low or too high instead of either one. So, on page 350 in your textbook, there's a great table that'll show you the null and alternative hypotheses for everything that we've done for the two-tailed and each of the two possible one-tailed tests. Highly recommend that table as a reference point. Now, we're going to talk about power and determining sample size so that we have a certain power. Now, another thing that we might be interested in is how we choose a sample size so that our test has a certain power. So the power of a hypothesis test is computed by taking 1 minus beta. Now remember, beta is the probability of a type 2 error. And for the type 2 error, we couldn't do that unless we picked a specific value for the mean to fall in our alternative hypothesis range of values. So in order to do stuff with this, we need to consider the true mean and our hypothesized mean with our null hypothesis. Now the difference between those two is delta. So delta is going to equal the true mean of the population minus the mean that we hypothesized it to be with our null hypothesis. So when we have a single tail, a one-tailed test, and a single mean that we're looking at, then what we do to find the sample size that we need to have the certain power test is we take our z sub alpha plus our z sub beta values, we add them together and square them, and then we multiply them times the variance of the population, and we divide by the difference of the true mean minus our hypothesized mean squared. Now, when we have two samples and we're looking at two populations, looking at the difference between two means, we can do the same thing. Z sub alpha, Z sub beta, those values, we can find them the same way. The only difference is we'll now multiply times the sum of the variance of each of the populations that we're looking at. And then again, we're going to divide by delta squared. Now you might be saying delta doesn't make sense that way, and it doesn't. When we have two means that we're comparing the difference of, delta is actually going to be the difference between the difference we hypothesized and the true difference. So delta is always the difference between the true value and the value that we hypothesized. Right? In the two-sample test, it's identical except for we know that we need to take the alpha, the significance level, and we're going to break it into the two different tails. So we'll be splitting it in half to create that critical region. So instead of having z sub alpha, we'll have z sub alpha divided by 2 for each of our sample size approximations. So that's how we can find our sample sizes for our hypothesis test to have a certain power in the one-tailed, two-tailed cases with just a single sample, single population, and with two populations where we're looking at difference in means. The other thing we want to talk about today is visualizing the difference between two samples, two populations. Box plots are a great way to do that. Now, you've probably seen a box plot at some point in your education. Box plots are a graphic that has the median of a sample along with the quartiles of the sample and the min and max extremes of the sample all plotted out. And we can see if a sample seems to be significantly larger than or smaller than another sample in its values that it takes based on where it is on a number line. So I want to just remind you and plant that seed about box plots, and then we'll look at them more with problems together in class.